Thanks to the committee for choosing the thesis. I'm really happy that someone liked this work. So my advisor was Hector Geffner, to whom I really owe this thesis, really inspirational. And let me dive directly into the context of planning a heuristic search. So the main challenges lately has been to devise new heuristic estimators, to devise new search algorithms, and also to devise new search enhancements in order to exploit the structure of the problem. So let me raise the fact that, don't worry.
All right.
No? It will work. It's just a short presentation.
I know my battery is not good.
So heuristic search planners, when they have to solve combinatorial problems, they perform extensive search. But it's annoying that in very simple problems, they still perform extensive search, and this doesn't make sense. And heuristic estimators are just one form of inference, but there are others that can be developed too. So can we infer more and search less? So the primary focus of the thesis was to formulate new ideas and new forms of inference that can be cost-effective. And the way that we validate it is by performing a fine-grained analysis in order to improve the scalability of planners and at the same time decrease the search effort. And theoretically, we try to understand why these inferences actually worked and also to characterize the hardness of the planning problems. So more or less, I will just talk a little bit about the first part and I will try to give more details about the second part. So as a result, there were 2 planners in the previous IPC competitions. Hopefully there will be another one in the next IPC competition. So heuristic based on the literal relaxation are used by the best planners. And however, even in simple problems, they give really bad estimations, misleading estimations, and also they suggest really bad helpful actions. So the way that state-of-the-art planners overcome these pitfalls is by using multiple heuristics in order to leverage the failures and the estimations, and also using multiple Q search in order to interleave helpful and non-helpful actions. So can we do something different, some structural inference maybe, instead of numerical estimations? So let me show you this example. It's the tower domain, and I think that everybody's familiar. You have a bunch of blocks in the table, you want to make a single tower, and normally the lead-based relaxation heuristics, they say that all the pcaps are helpful in the initial state, which doesn't make sense, and all the pcaps result in the same cost estimate. So something is wrong there. But the relevance of all the pcaps result from the chain that you want to pick a block in order to hold it, because at some point in the future, you will stack it in order to achieve the goal. But there is a way to prove that these kind of chains, or paths that we call, they are impossible in every plan starting from the initial state if they are understood as sequence of causal links. Therefore, we showed in the thesis that wrong pickups and many other domains, other actions, can be pruned in structural grounds instead of numerical grounds. So we formulated and tested a hierarchical planner that reasons over causal chains or paths and is built on top of 3 notions. By enforcing the semantics of causal links, we show that some paths are impossible in a given state, and we call this path consistency. So if a path can be extended into a plan, we take it and we decompose the problem into subproblems. And finally, we also introduced a heuristic in order to choose which are the best paths in order to commit and decompose the problem. As a result, the C3 planner performed pretty well. It solved 78% of the problems backtrack-free, suggesting that this kind of reasoning actually can help. And another important issue is that we realized that most of the benchmarks are decomposable. So the next thing that we thought is, okay, C3 is incomplete. Can we come up with a complete planner that reason over plans instead of paths, and taking the advantage that problems are decomposable, can we also serialize the goals of the problem? And there are many other ideas like helpful actions, landmarks, that are also old ideas that can be integrated into a state-of-the-art planner, but that still solve most of the problems backtrack-free. So that was the question. And what we proposed was the planner probe that extends a standard greedy best first search by throwing a probe from each expanded state from the greedy best first search. And a probe is nothing else than a single action sequence that is constructed greedily. So the challenge here is actually how do we compute, or how do we build these probes so easy problems are solved without search, or at least with almost no search. So probe, a single probe, is an action sequence that is constructed greedily by doing three things. First, you just choose a subgoal to go. Once you have chosen the subgoal, you iteratively choose the actions in order to achieve it, and at the same time, you keep and you post the reasons, which we call causal commitments, of why every action has been chosen. If the probe succeeds, the problem is solved, and if it fails, it dumps all the expanded nodes into a greedy best first search, and another probe is thrown. So how can this perform? So this table, I won't go into detail, but the rightmost columns show the coverage of a single probe over previous IPC domains, and you can see that 70% of the problems are solved directly, just a single action sequence. And when you plug it into a greedy best first search, the coverage jumps up to 92%, which is competitive, was competitive at the time with other state-of-the-art planners. So C3 and probe are just an experimental validation that inference over the structure of the problem can pay off. And planning is complete, but most of the planners solve the problems in very few seconds. So can we explain why C3, probe, Llama, and all the planners that we have perform so well? And more importantly, can we characterize which is the line that separates easy from hard problems? So our answer for that is a new width notion and an algorithm that is exponential on the width of the problem. And the explanation that we found out is that the benchmark domains have small width when goals are restricted to single atoms. And when you have joint goals, conjunctive goals, normally they're easy to serialize into atomic goals. So if you want to have hard problems, just find problems with high width, and there are no benchmark in this class, or just consider multiple goals that are not easy to serialize. And for example, there is Sokoban, and there are many other examples. So let me introduce first the algorithm that achieves these bounds. But before, I have to introduce the notion of novelty. So the novelty of a state is the following. As we will say that a state generates a new tuple of atoms if it's the first state that make the tuple true, and no other state in the search have made true before. Okay? And the size of the smallest new tuple that the state generates is the novelty of the state. If there is no such tuple, the novelty is the number of variables. So let me rephrase it. The novelty of a state is the smallest tuple that the state makes true, and no other state in the search have made true before. Nothing else. And the algorithm is just what we call the bounded iterative width, is a breadth first search that prunes newly generated states whose novelty is greater than the bound. And the iterative width algorithm is a sequence of calls to the bounded iterative width that, if it solves the problem, it will run in exponential time in terms of the width. So the key theoretical property here is the following. The iterative width algorithm solves the problem optimally in time which is exponential on the width of the problem. So you may ask, how actually does it work this? So, well, being simple and blind is just a breadth first search that prunes states. It's very good. It's a very good algorithm when the goals are single atoms. And this is no accident because the width of the benchmark domains in planning have small width. So we tested the instances from previous IPCs, and for each instance with n goals, we generated n instances with a single goal. And the results are remarkable. You can see here we had 38,000 problems, and we compare iterative width with two other blind search algorithms and a standard baseline heuristic search planner. And the performance of iterative width is comparable to a simple heuristic search planner, which was surprising for us also. So the primary question then is like, okay, atomic goals, not the planning problems, normally they don't show these features, they have conjunctive goals. So can we do something with the same algorithm? And the answer is actually yes, there is a really simple way that we can use the iterative width algorithm in a form of hill climbing over the goals of the problem. And the idea is the following. You just start in the initial state, you run the iterative width algorithm until you reach a state that achieves a single goal. Once you have this state, you jump to that state, and you run again the iterative with until you reach a state that achieves the previous goal and a new one. And you keep doing the same until the problem is solved. So if there is a solution, the sequence of plans for achieving a new goal each time is just a solution for the original problem. So obviously it's an incomplete approach, it's just hill climbing over the set of goals, but we use iterative with for both decomposing the problem into subproblems and in the same way to solving them. And it's just a blind search procedure, there is no heuristic at all, and moreover, the important thing is that iterative with does not even know which is the next goal to go. It just bumps into it. So how good does it work? Again, it's better than a greedy best first search with the additive heuristic over conjunctive goals. So in this table, I won't have time to go through it, unless you really ask me to, but there is like a column that it says the coverage, the quality, the time. This is the maximum and average width for the subproblems. So you can see that the subproblems, single goals are really easy to solve also. And you can see that the last column, the coverage is better, the quality is better, and the time is better. So it really outperforms a baseline heuristic search planner. So what is actually this width that we are exploiting here? Let me try to give the intuition. I will try. Consider a chain of tuples, okay? And each set of each tuple is a set of atoms from the problem. And we will say that a chain is valid if the first tuple is true in the initial state, and all the optimal plans for each tuple can be extended with a single action into optimal plans for the next tuple. Okay, so first tuple, true in the initial state, and all optimal plans for each tuple can be extended to optimal plans for the next one with a single action. And we will say that a chain implies the goal of the problem if all the optimal plans for the last tuple are also optimal plans for the goal. And the size of the chain is the size of the largest tuple in the chain. So it's not the number of tuples in the chain, it's the size of the largest tuple in the chain. And the definition of width is that the width of the problem is the size of the smallest chain that implies the goal. That's it. So we proved that domains like block words, logistics, gripper, M-puzzle, and some others have bounded width that is independent of the problem size and initial situation, provided that the goals are single atoms. And these domains actually have one or two, the width. But you can imagine that establishing the width by hand, finding this chain for every single goal, for every domain is really tedious. And if you want to do it automatically, it's as hard as optimal planning. But yet, we used what we did in order to assess how complex are the width of the problems. We used what we call the effective width, which is the first bound for which the iterative width algorithm finds a solution. And in the worst case, it's exponential on the real width of the problem. So these are also the single goals for all the domains. And what you can see here is that 37% of the single goals have effective width 1, which is very surprising. 51% effective width 2, and just 11% have an effective width greater than 2. So for an algorithm that is exponential on the width of the problem. So just for summarizing a little bit, the iterative width is just a sequence of novelty-based proven breadth of search that is excellent when goals are restricted to single atoms. And the reason for that is that such problems have really low width, and the algorithm runs exponential on the width. And then if you try to serialize using the iterative width in order to attain the goals one by one, the resulting algorithm is faster, has better coverage, and finds much better plans than the standard greedy best first search planner. And the intuition for that is that the goals are normally easy to serialize, and the atomic goals that are found by the serialization have also low width. So the last question that we try to answer is, can we integrate these ideas with other ideas in planning? And our last contribution was just a pure best first search planner with a single evaluation function. So it's nothing else than best first search and this evaluation function. And what the evaluation function says, it takes into account the novelty of the state and if whether the action leading to that state was helpful or not. And the combination, if the novelty can take the value of 1, if the novelty was 1, 2, upon 3 if it was greater than 2, the novelty. And the range of values is 1 to 6. And what we did is we prioritized by the number of unachieved landmarks, which help us to achieve kind of a serialization, and also with the additive heuristic. So everything is there in the evaluation function. And the important thing here is that the novelty of the state is computed over the states generated that have the same subproblem, and by same subproblem I mean that have the same number of unachieved landmarks. So it's very simple, best first search with this evaluation function, and it turns out that actually it's competitive with the last version of Llama. It solves just few more problems with better plan quality, and time, in terms of time, is competitive with Llama. So again, the more details can be in the thesis. And let me conclude just by reminding you the contributions. We provided a way to reason through causal chains and paths, the notion of probes, which are a fast mechanism for doing a look ahead. As a result, there is a C3 planner that solves many problems backtrack-free, probe, which is a competitive state-of-the-art planner, which also solves many problems backtrack-free. And then we try to explain all this behavior by coming up with this new width notion for planning problems and domains, a proof that many domains have low width when goals are single atoms, a simple planning algorithm that is exponential in the problem width, then a blind search algorithm that combines iterative width and goal serialization and is competitive with a baseline heuristic search planner, and finally, a best first planner that integrates these new ideas with old ones. And if there is something that I want you to keep in mind is that maybe sometimes it pays off to infer more, search less, and serialize the goals. I want to thank for all the support and advice to Hector Geffner. This wouldn't be able to do that without him. To the fellow PhD students, Alex Albore, Emil Keider, Palacios, and Miguel Ramirez, the ICAPS community for all the support and all the advice from many people, my family that are here, Sergio, Monica, and Maya, and of course also to Jimena Zula for everything. And yeah, that's it. Hope you enjoyed.